Hi folks, welcome to my Bit Retro Journal. Today we're going to look at programming on an old 80s computer and what you can actually learn from that. So back in the late 80s, early 90s, when I got my QL, along with it I got the digital C compiler, which was a small C compiler. And then a few years after that, I actually got this textbook. I think I bought this in the 90s. It has a date of publication of 1988. But what's cool about this book is that it basically goes through the entire small C compiler, which is what digital C was based upon on the QL. And not only does it go through and talk about how it was developed, it actually has the source code at the very end. So that's pretty cool. So you actually get to see, you can see that, yeah, there's the actual source code. So, and you hear a lot about, one of the cool things about 80s computers is that they really taught us how to code, not in BASIC per se as much as because a lot of us learned how to program in machine code. My first computer was the ZX81, and one of the books that I got with that was Mastering Machine Code on Your ZX81, which is a terrific book that really sort of started me on the path of becoming a coder. And what was amazing about that is it talked about a hidden language in this computer besides BASIC, and that just intrigued me to where I learned, oh, that's machine code. And of course, the ZX81 didn't have a machine code loader, so you actually had to, it didn't have an assembler built in, so you had to poke in the values and then run it. And yeah, I learned a lot from that. However, I went to school. When I came back from school, I had really taken a liking to programming language development, compiler construction. And so I also was able to relate what I learned with machine code to the higher level languages. So in other words, if you know how a programming language works, you can actually manipulate it to improve its performance. And I did that. I did that in the on the QL. In fact, I think I have a program. If I were to, let's see, this is 4, 5, maybe 7, where I had my terminal program, and one of the first things I had to do in that was to learn how to optimize it because it was running too slow. I knew generally how control structures like switches and statements and ifs worked. When you put a break in a case of a switch statement, it would jump to the end of that. But if you were at the end of yes, I don't have, oh, there's the source code right here. All right, let me load up QED and load term C, and then we can take a look at it. And so basically there was these what's called cascading jumps in machine code that a compiler might generate if it's not optimized, where you jump to the end of a block right away to jump again to the end of the block if you have a nested set of ifs. And I'll show that as a later example, but also in a switch statement. So if I go MDV8, term, and I'm going to zoom in on my when I actually start programming, so hopefully you can kind of see it a little bit. This is just a general example, but I'll put the camera literally right in front of that when I'm ready to go. I just wanted to demonstrate here. If you look at this is my terminal program that I wrote, and in the main body of it, where I'm going through the critical loop that's grabbing characters from the modem where it had to be fast. And this is in public domain if you want to take a look at it. Contact me and I'll let you know where to find it. So most of these functions are just to sort of get everything ready. So I think the main function is on the bottom. Yeah, right here is the main function. While connect, and then basically there's this big switch statement in here. And this switch statement is going to give me all. So if it's any control character, then I want to manipulate the switch statement, right? So case 13 would be a carriage return. And then new line, and etc. Right? So there's I forget what 26 is, but there was a bell too. There was up, down, left, right. So that's what all these things do. Beep. So controls. ASCII character 7 is beep. You can see that right there. It says beep. And so, but if you notice at the end of each of these statements, maybe I'll point to it with a pencil, there is a go to read keyboard. Well, generally what you do in switch statements is you do a break. And what a break does is it goes to the end of the switch statement, right? But notice at the end of the switch statement, which is right here, I'm in a nested else. And so basically the break would have jumped from here to the end of the switch and then had to jump all the way past the else. So a second jump would have happened. This is what the cascading jumps are. And so instead, I jumped the else with a label and just went to it straight there. That saved me a jump, and that actually helped me keep pace at the higher baud rates. And so, again, knowing how programming languages structures are actually implemented in machine code. Now you can easily look at the disassembled code, but also just knowing, having been in a compiled construction class, knowing how code is generated. I didn't even ever look at the machine code that was generated. I just sort of inferred that, yep, that's what's going on, because that's just, I didn't imagine that the C compiler on the QL was optimized enough to be able to do that. Now, granted, on a modern computer, and I'll give you a Linux example here today as well. It does a lot of optimizations, and it might actually do that, get rid of the double jumps and do what I just did by hard coding it in. But there's no harm in doing it yourself if you really want a tight loop on a slow machine. But anyway, that's what you can learn from this. So it's not just that you can only learn machine code programming, you can also learn to become a better coder. And I'm going to give you an example of this today. I've learned a lot when I developed my basic interpreter that became a command shell on the Mac, and now is the basis of the ZX simulator. Back in the 90s when I wrote it, I learned some of the ins and outs of the small C compiler, knowing that, for instance, two AND conditions, if A is greater than 10 and B is greater than 20, actually generates more code than if I just go and string two ifs together. If A is greater than 10, if B is greater than 20, because they accomplish the same thing. So the AND has to be a bit more flexible because it doesn't know if there's going to be an OR in there or not. But if you know you just have two ANDs, you might as well just string them together as two ifs. Now you can't add an else to that, but at least if you just have an if with two ANDs or three ANDs even, you can just string together two or three ifs. It actually does the same thing and it generates less code. So I learned, and also learned on small C, for whatever reason, the for loop, just a simple for loop, is less efficient in terms of code size than the equivalent while loop. But with a while loop, you generally initialize I equals 0 while I is less than 10, and in the body of the code, you increment I++ at the end. That's what a for loop actually should be, but for whatever reason, small C, when you do that, those two loops and compile each of them, the for loop is just going to take up more space. And I don't know why that is, and I haven't really dug into that in this book too deeply. But so I've learned to use whiles instead of fors, even though I'm a big fan of using fors when you have a number of items that you're counting. You should use whiles when you don't know what the end condition is. But when I'm programming on the QL, just through my experience, I tend to use a while instead of a for, just when I care about my codes, the binary code size. And that's just from experience. What I want to show you today is the impact doing these kind of optimizations can have in terms of runtime. And then I'm also going to show that to you on a Linux system running, Ubuntu running GNU CC, pretty, maybe 2 or 3 years old. Just to show you what the difference there is, okay? So that's what I'm going to do today. And so I'm going to change my camera to point straight on the computer so you can see better what I'm doing. Okay, let's go ahead and do that. Okay, so I'm going to create a new file, mdv3, let's call it speedc. And yeah, so let's do some C coding. So always include your standard IO, and again, using the underbar because it's the QL. We are going to create a main function, and let's create some variables. I'm going to use long so I can have larger, short is 16-bit integers on digital C, long is 32-bit. So that way we can have numbers bigger than 32,000. All right, so increment the time in 3 variables. So we're going to set these 3 variables to 10, and then we're going to set our time to, there's a date function in digital C that gives you the number of seconds for the date. And then our for loop, we're going to go, let's go to 1,000,000. So it runs, and that's our loop. After our loop is done, we are going to print out the stop time, % LD for long decimal number, integer number, and yeah, and then we're going to say current date minus previous, and that should give us our time. And so all we want to do next is we want to add an if in here. If a equals 10, which is always going to be true, do something, otherwise, since this is not ever going to be executed, it's very simple. I'm just going to stick it in a single line. I'm putting the block parentheses around just so you can better see what's going on. And then outside of everything, we're just going to increment C. And then inside of the if, we're going to have another if. And that's sort of the nested if that shows the optimization. And here we're going to have an if else. And they're just going to be short. So I'm going to increment if it's true, which it will be. So, so the C minus minus should never actually be hit. Otherwise, C minus minus, which gets skipped over each time. And I think that's the program. So you have, yeah, looks good. So you have a for loop from 0 to 1,000,000, less than 1,000,000. If A equals 10, which it is, then we go if B equals 10, which it is. And then the optimization actually happens right here, right? So most compilers would optimize saying that once you hit this, if you just exit out of this, you jump over the else, but then you have to jump over that else. So it's 2 jumps. So what I will show you after I compile this, the basic one is if I put a jump in here, a go to, that I can optimize it. Now most modern optimizing compilers can do that, but here it does not. So I think that is the code I want. So let me actually save it. I don't think there's anything, yeah, it's all there. I don't see a bug in it, so let's quit. And let's, I'm not going to have you sit through this because you've already seen me compile a bunch of times. So what I'm going to do is I'm going to compile it, and then I'm going to run it a few times just to get an average number of how many seconds it takes to run the thing. Run it maybe 3 times to see if it is pretty consistent in terms of what it does. And then we will make the modification, see what happens. All right, so I'll be back on that. Yep, so I've run it a few times. Generally, it hits either 216 or 217. Mostly hits 216, so 217 was actually the highest value. I ran it 3 times and I got 216 twice and then 217. All right, so what I want to do next is I'm going to go back into QED and make the change and then run it again a few times to see how that impacts the speed. And then we'll also take a look at the size after we do all that, just to see how it impacts. My assumption is it's adding an extra jump, so code should be slightly bigger. But let's worry about the speed first. So here it is, and so MDV3 speed C should load pretty quickly. All right, so what I want to do is I want to add a skip in here. Right here, I'm going to add in a go-to skip. And I know, I grew up, when I went to school, I learned go-tos are evil, so don't use them. And it's true, you shouldn't use go-tos, but again, I'm doing this in a very specific manner, which is to speed up code. So here, I'm getting rid of the double jump by just saying go to, so instead of having it go from here and then here, it's going to just go straight to there. So it'll probably leave that jump in after here because I can't control that. But an optimizing compiler would get rid of that, but so this is going to keep it in. But yeah, it's only a few bytes, 2 to 4 bytes for the jump, so I'm not too worried about it. So let me again save this. C lets you put in labels, and that's all this is. Basically, it's an identifier with a colon after it, and then you can do a go-to that label, and it works just fine. All right, let's go back, and again, I'm going to compile this and run it about 3 times to see what that gives me, and then we'll know if the hope is it's faster. It should be faster because I'm not doing that jump a million times. So what sort of speed gain do you get by not doing a jump a million times? It'll be interesting. But again, I'm not going to make you sit through this, so I'll come back when I have the thing run. Okay, here we go. I ran that 3 times, and it did. One of them came back as 213 seconds, but 2 of them as 212. So it's about a 4-second difference between the two. So what I want to do next is actually compare their sizes, and instead of using ICE, I'm going to use Toolkit 2, just because it's kinder on the camera not to have to switch between the white and the green, etc. So and what I have to do is run a command, because I don't have, since I have ICE on here, I don't have Toolkit 2 in the ROM, I have it in RAM. So I just have to go, I forget now what to type. Dir MDV7. It's on MDV7. I didn't want to load it in beforehand because I wanted TK2 boot. I wanted both. What I did is I rebooted the machine for both runs and ran both speed tests with executable, so they had full control of the machine. So what I want to do is run MDV7 Toolkit 2 boot, and that will load the Toolkit 2 command so that I can do a wstat, which will give me the size of the files. And so I can just do a wstat on here we go, QJump. So this should have been part of the QDOS back in '84, but Tony Tebbe left because he was worried that he released it a little bit too soon, and then he finished writing that Toolkit 2 ROM update. And so if I can do a wstat on MDV4 speed, it should actually wildcard, well, the object. Yeah, here you go. So speed 1 and speed 2. So speed 2 was the with the skip, and surprisingly, they're the same size. Well, that's very odd. I would not have expected that because I added a jump in there. So why would it have? I don't imagine Digital C would optimize things. So let me do. I do have the book, so I can try to live through that to see if, because it does show the code, to see if I can figure out if it does an optimization. But that would be pretty cool. But let me do this first. So I'm going to exec. I'm not going to run this next one. I'm just going to change it. So exec MDV3. I'm just going to change and compile it to see if it actually increases the code size if I move the skip to a particularly different location. So maybe this does some sort of optimization where it sees that there's a jump at the end of the then part of the if, so that it doesn't put in a double jump when it sees a jump. That would be pretty cool. I'd have to see how they did it. Not something I would expect from a 1980, late 80s compiler, but I think 87, 88. MDV3 speed C. So what I want to do here is just make that addition to, so I'm not going to run this because I'm actually literally now, so the code with the skip and without, we're doing exactly the same thing. This change will not, so it's no use running it. I would guess that this would actually become bigger, not smaller. So if it actually made it smaller, then I would be really impressed in terms of this compiler optimizing. But I just don't think it would be doing the optimizations. Let me do that. MDV5CC. And yeah, so I'm just going to compile it, and then we're going to do the wstat on that again and see if the code size shrinks or grows. Again, I'm assuming by 2 or 4 bytes it should have grown. Surprised that the speed test without that did not grow, but again, I'm not going to make you sit through this, but yeah, so let me do that. So it's finished compiling that one, so I'll have to reload MDV7 TK2 boot, and then we're going to take a look at, I want to look at speed 2 versus speed 3. Speed 2 was 2568 bytes, so you would expect speed 3 to, I think it would be 4 bytes because I think it's a 20-bit address bus, so you have to at least have that plus the actual jump instruction, which might be 8 bits. So let's see. So if I do a wstat on MDV4 speed 3, that gives me, yeah, and wstat MDV4 speed 2 gives me, and wstat MDV4 speed 1 was the first one. So that was yeah, so I was surprised that speed 1 and speed 2 were the same size, but speed 3 is 4 bytes larger because we moved the skip ahead of the C++. So it looks like, yeah, it looks like it optimizes. I'll have to, let me check the text to see if I can figure out where it does that. So I actually found it. Let me see if I can zoom in here so you can see what's going on. So this is the do if part right here. It basically sets aside 2 labels that it perhaps uses. It does the test of the conditions and jumps to label 1 past the statement. Otherwise, it executes the statements. Here, it checks to see if there's an else. If there isn't, it just generates that label 1 and then returns out of it. Otherwise, it gets the label for label 2, and here's where it generates label 1. So basically, if there's no else and the if is false, it jumps here. Now, what's interesting is if the if is true and there is an else, it does this if test right here. And oops, it does this if test right here. And that's where your optimization, that's your optimization. Basically, it says it has this global variable last statement that says if there's not a return, there's not a go to, then generate a jump to label 2, which is down here. If there is, the last statement is a return or a go to, then there's no reason to generate that jump, and then it just continues doing what it does. So it saves adding that jump statement because it sees that there's a jump for return or go to already. So that's pretty cool that it already did that optimization back in the mid 80s. So that was unexpected. And I've had this book since then. So what we're going to do next is we're going to let's zoom back. I'm going to now put the camera back here, but this time have a Linux window showing you and repeating the same stuff using GNU-C on an Ubuntu server, all about 2 or 3 years old. So it's not the latest and greatest, but I mean, for the purposes of what I want to show, it should be fine. All right, so let's go ahead and do that. I'm on a Linux system, and I have, so let me just move my cursor to the bottom. If if I do, it's an Ubuntu version, and it's about 5 years old or so. So let me actually go ahead and type in the program. I'm going to use Nano, which is my favorite editor. Well, I like Emacs, but I don't have Emacs in this thing. So stdio, we're going to do the main loop. And here we're going to have a very quick, so again, we have the I, not the T, the A, the B, and the C. Actually, I could have the I just be local to the for loop, but I'm kind of keeping that. So I'm not doing the timing in here because it doesn't have a nice date function that returns a long. ABC equals 10. Sorry, and then for I equals 0, I is less than, and here I'm going to do 10 billion, I think. Right? Yep, I think that's 10 billion. So get rid of that, and then I++, and we're going to close that loop up. And then inside the for loop, we're just going to have an if a equals 10, which is always true. We're going to have a bigger body, and we're going to else. And here, again, we use the same technique, C minus minus, just to keep the code more readable. Oops. And then outside this whole thing, there's going to be a C++, and then if B is equal to 10, which is always true, then we're going to say C++ else C minus minus. Okay, I think this has no bugs in it, so I mean, it's a pretty easy program, right? So let's see if this will compile on the first go. And then I'm going to go gcc speed.c-o speed1. And it compiled. Word count dash b speed1. Word count. I forget what it is. I mean, if I just do speed1, yeah, it tells me it's lines, words, characters. Is it -C? I thought I did bytes. Yeah, -C. So that's how many characters are in there. So before I run this, let me actually go back into Nano and make the optimization. Go to skip. And we're going to then say skip : all right? So save that and recompile that as well to call that speed2, word count -C speed2, word count -C speed ? So they're both the same size. Okay. So it does a similar optimization to Digital C, which is expected. Let me do one more, which is now I'm just going to move this C++. And the expectation here is that the code should actually get smaller, right? Since it should know that the C++ never gets hit. So it'll be interesting to see what happens. And we're going to compile to speed3. And then let's just do the word count of all of them. And surprisingly, it's the same size. So it didn't actually optimize that. Interesting. So there is a way to get gcc-q help equals optimizer, or is it plural? Plural. And I can grep for all the enabled ones. And the beauty of Unix. Yeah, and so it has delete null pointers, inline atomics, loop optimizations, critical path heuristics. You'd think that would take care of that. And there's 2 pages worth. I can also get and just look at disabled, and there's a bunch that are disabled. line function, line jumps, probabilities, exclusive, stack adjustments, registers, follow jumps. Yeah, so you have a lot of exclusions, and I don't know of an easy way to turn them all on, but I think did my system just hang? Oh no, one more time, sorry, I don't know what it was doing. Disabled. Yeah, so a lot of them are disabled. Okay, what I will do is, and I'm not going to have you sit through this, I'm going to run all two, speed 1 and speed 2, and I'll alternate between them. The way I'm going to run this is I'm going to say date, speed 1, date, I have to make this local. And that should basically run this and then give me a difference. And then I'll do speed 2, and I'll alternate between speed 1 and speed 2 and give you sort of a final number of what I'm getting. Again, it's going to vary because it's multi-user, but with 10 billion, it should be pretty big enough difference. So, all right, so I'll come back. And here are the results. I ran each of them 5 times. So I tried to alternate them, although there was, on one occasion I ran the same one twice, so I ran the next one twice as well. But so they're pretty close. I mean, they basically are separated by 2 seconds because speed 1 ran twice at 3 minutes 34 seconds, and the slowest for speed 2 was 3 minutes 33 seconds, although their fastest was the same, 3 minutes 32 seconds. However, I had another idea, and actually it was the quickest way to test this. If I just do a diff on the object code, they're actually the same. And just to demonstrate that I didn't screw up, you can look back in the video. All right, well, I hope you found that interesting. So again, there's definitely things you can learn from programming on an old computer, because both space and speed are diminished, and so you have to be a little smarter. But all the things that I learned back in the early late 80s, early 90s about coding on that, still I use today in terms of when I write code. I like to write efficient code, even if it's a slow language like Java. I think about these things, and even if the compiler does the optimization for you already, no reason not to add that code anyway, just to be safe, right? So I'll end there today. Thanks for joining me, and I'll see you next time.